questions for today. And I've got, I'll show you. I'm going to experiment this week with something for homework, so don't hand it in. We'll see. Yeah, hang on to it. But 2.6 first. What sorts of issues did you have, if any? We can go over them. So you said 2.6 was your favorite. I heard people saying that you wanted the quiz to be. It was tedious. There's some tedium. So, okay, well, maybe not. That's fine. Yeah, oh yeah, what do you think? Number 3? Yeah, sure. Number 3. Let's take a look at 3. So once I get it written, I'll put my book down. Okay, so we've got y prime equals y. Y prime equals y. Y of 0 is equal to 1. Our target is y of 1.0, and we're supposed to use h equals 0.1 and h is equal to 0.05. So the 0.0, both of those are quite tedious. So I'll do one of them, and then we'll just call it a day, if you will. So here's the deal: is you're going to make a little chart, and we have I don't know, x, and then we've got the function. So this is, maybe I'll do it this way: m is equal to the function xy, and then I don't know what else I need to do. So let's start with, we're starting with 0. Oh, I need my y value, y, and then we'll have the slope is equal to the function. So that's this thing right here. Okay, so y is equal to 1, x equals 0. The slope at that point is 1, because the slope is equal to 1. And then the next point, so this is the key, is the next point. So x, whatever, I plus 1 is yi plus 1 is the old point plus however far you're moving times that slope, times the slope, I guess, times the function value. So you just figure out, like, where are you? What direction are you going? How far do you have to go? And then you get there. So in this case, my h is 0.1, so my next point will be 1.1. So I'm going along 0.1, 0.2, 0.3, etc. Now I've got 1.1, and of course the slope is 1.1, but I'm going to do this: 1.1 plus the 0.1 times the slope. Wow, this one's actually quite boring. 1.21 plus the h times the slope. And since the slope is equal to y, that's why this is kind of boring. 1.331, 1.331. How far do I have to go with this? You gonna make me go all the way? So this is 1.4641, 4641. So anyway, yeah, this gets quite tedious. You would do, let me see if I can do it more quickly on a calculator. Since we're doing the same thing over and over again, you might be able to get away with just hitting enter repeatedly. I don't know where my calculator went. It's over there just a minute ago. So here we go. Let's try this. So yeah, let me see if I can do this more quickly on the calculator. So on the calculator, if I were to do the second part, see, I'm not even finishing the first part. So we have x and y. So we start off with this. The next point is this. So then we have the slope, which equals y in this case. And then you do 1 plus 0.05 times 1. Okay, so just a sec. 1 plus 0, start with just 1. And then that plus 0.05 times that. Okay, I'll show you what I did. This is fun. Hold on a sec. Camera land. There we go. Let's zoom in. There it is. Okay, so that is the first. So it's 1. because the y value is the slope, you're doing the y value is the first ants, and then the h, that's how far you're moving, times the slope, that's the second ants. But because the y value and the slope are the same, you can just do this. And then actually I can go through, that's the first, so I need 20 of these. So that's number 1. So here's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Whew. Okay, so that would be the last one. So that's what your table would look like if you were to do this. I know that's tedious. I think I saw that when I was assigning things, and I thought that's tedious. I don't know why I didn't. Did I tell you to do both parts on that one? Oh, I guess it's not A and B. I think I thought you should only do A, like the h equals 0.1. Sorry. Yeah, 4 would be more interesting, but also more work. All right, does that answer whoever it was? Was that your Joshua? Yeah, it's just tedious. Tedious. Okay, let's move on then to 3.1, which is more exciting because you're dealing with applications. And this was broken into 2 parts. You had growth and decay, and then you had the Newton's law of cooling. So let's do growth and decay first, see if there are any issues with that. Hopefully it was pretty straightforward, but there might be some algebra that you want to talk about. What do you think, Luke? 13? Was that a growth and decay? No, that's a cooling. We'll come back to it. We'll do it in a minute. Anything from the growth and decay? So the growth and decay was, okay, so let's do cooling. Okay, we can always go back to the growth and decay if we need to. So 13, let's do the Newton's law of cooling, which I had a fail last time. I was so embarrassed. I mean, well, no, it wasn't embarrassing. It was just not as close. I was hoping that I'd be closer with my prediction to the truth with that coffee cup. I don't know what went wrong. Okay, thermometer is removed from a room where the temperature is 70 degrees. Okay, so T of 0 is 70 degrees. That's what they're saying. And taken outside where the air temperature is 10 degrees. So that means T sub M, is that what we use for ambient? Is 10 degrees. Okay. After 1/2 of a minute, the thermometer reads 50. So T of 0.5 is 50. What is the reading of the temperature at 1 minute, and how long will it take? So I want to find T of 1, and I want to know T of what is 15. So there's all the stuff that I'm going to do. This will be part A, this will be part B, even though it's not labeled as such. Okay, so first things first, we need to write a differential equation, and actually this is a good one to choose because the quiz is sort of similar, not quite as complicated, and I actually give you the formula. So the formula, I actually have this, dt over dt, and it's probably shouldn't have done this, but oh well, there. So there's the, should be Tm, shouldn't it? Yeah, that's labeled incorrectly. Good thing I checked. Okay, so this is the Newton's law of cooling says that the rate at which you cool or heat an object will be proportional to the difference in the temperature of the object and the ambient temperature. So let's go ahead and do this. dt over d little t is k times t minus 10. So that means that we have this natural log of t minus 10 is equal to k times t plus constant. I know I'm kind of skipping a few steps here, but we did this part. So here, this is separable. Solve. How's that? So skipped a couple of steps there of doing the separation of variables and then doing the integrals. And then we'll do this part. This is going to be C1 e to the kt. So once again, I'm kind of cheating a bit, not too much. So t is equal to C1 e to the kt plus 10. Okay, so that tells me that C1 should equal 60. And the reason I know this is because T of 0 is 70. So for that to be the case, So I've done all the easy stuff. Hopefully that isn't too much of a stretch to do all that in my head. You can kind of see here that if this is 60, then when you plug 0 in here, you get 70. That's what we want. So let's get now where we are is this t of little t is 60 e to the kt plus 10. So let me pause there because that's, I know I just went through a bunch of stuff super quickly and maybe that was too quick. So anything there that you're like, what? Where'd that come from? Explain. I could probably find the slide and read in monotone the slide from the last time if you prefer. I'm just kidding. Sorry. Okay, so next we're going to deal with this thing no, not that thing, this thing right here. It says that after half a minute, so t of 0.5 is equal to 60 e to the 0.5k plus 10. So that means 50 is equal to 60 e to the 0.5k plus 10. So this is going to be 2/3 is e to the 0.5k. Okay, what did I just do? I subtracted 10 from both sides. I got 40. I divided both sides by 60. 40/60ths is 2/3. Okay, so that means that the natural log of 2/3 is equal to 0.5k, and k is equal to 2 ln of 2/3. Let's find out what that is just for fun on this calculator that I've hidden somewhere. It's on the other side. I see. Oh, that's right. There it is. Very nice. Okay, so let's see. 2 times the natural log, or that, no, that's just going to be the natural log of 4/9. 4/9. That's the cool way of doing it. So that's going to be negative 0.8109. We'll go out to 4 digits. Okay, so that means we have t is 60 e to the negative 0.8109 times t plus 10. All right, let's answer the 2 questions that we have. Number 1, what temperature will it be in 1 minute? Is that right? Is that what it says? It's 1 minute. Yeah, 1 minute. Okay, so we'll do t of 1 first. So 60 e to the negative 0.8109 plus t, which is approximately, sorry about that, so 60 times e to the answer plus 10, and I'm getting 36.6666. Wow. So interesting. Oh, I understand. Okay. Yeah, this is 60 times 4/9 to the t plus 10. E to the negative, let me double check. E to the negative 0.8109. Let's see. E to the negative 0.8109 should be about 4/9. Whoops. Sorry. E to the negative 0.8109. Yeah, 4/9. So whatever. But anyway, yeah, there it is. So that's going to be after 1 minute. And then if we want to answer the question, what will the when will the temperature be 15? It'll be this. So that's 60 e to the negative 0.8109t is equal to, plus 10 equal to 15. So 5 over 60 e to the negative 0.8109t. That gives me this is equal to the natural log of 1/12. I got it right now so far? So it's going to be the natural log of 1/12 over 8109. Let's see what we get. So natural log of 1/12 divided by negative 0.8109 109. And that gives me 3.06. Good enough. 3.06 minutes. All right. Yeah, sorry, I kind of glossed over that. Whipped through it way too quickly, but it gets so I guess Luke, you're the one that wanted me to do that. Any other questions about that? So you got that clarifies. And I don't know how many of the others of these I assigned. I can't remember, but it's all going to be sort of similar. You're using the same thing. It's this formula up here. And I've got the formula printed on the quiz. It's kind of, why did I do that? I don't know. Wow, everyone's packing up. You want to do the quiz. Hang on to your homework so that I can give you more instructions about that. But for now, let us give this one a go and see how it goes. Here you are. Here's some. Is there 3 there? I don't know. I'll come back. That's not enough. I'll give you one more. You can fight over who gets the big one. Oh, okay. I'll come get them. Thanks. Oh, you dropped one here. Or is this the... No, okay. No, it's all right. Did I give you one? I didn't give you one. Here, you want one? Here, you can have the rest. Is there enough there? There might not. I've got some big ones. I'll give you a big one. Here. Oh, I've got one more big one. What's it? What's this? Here. Okay, good job. Let's see, for those watching. So don't forget to change the 0. So I'll zoom in on this. You can see this typo here. How this, the ambient temperature, whatever, the TM. Ready. All right, hopefully you're coming down the home stretch. It looks like some of you are all done. So if you are done and you want to share, I could take a look and see if I got it right. Okay, excellent. It's always exciting to see things that are the same as other people's things. You're all set? Very nice. Excellent. You're all set? Very good. Interesting. Sorry. Take your time. No, take your time. I know you like to meditate. Actually, Joshua likes to meditate as well. You didn't. You just were like, get it gone. Yeah. Nice. Nice. Excellent. Just looking. You've got a good function there. Beautiful. I love it. All right, so those of you who are still enjoying the process, maybe you can try to wrap things up in the next minute or so and put down an answer. All right, excellent. Nice. Oh. Oh, wait, you did this all? I've got calculators. It's okay. I mean, you can do it by hand. It's just a little bit more painful, but I guess it's like a challenge for you. How's it coming back here? Very good. Very nice. Nice. I love it. Let's see. Whoops, sorry. There we go. Is this the right way to do this? Nice. That's all right. It's okay. You got an answer? You didn't box your answer? Oh, that's K. All right. Well, at least you got K. You could always, what you could do is you could just put down K, put it with the function, and just box that. I'll come back after you do it. Did you get it? I'm so close. Oh yeah. Yeah, very nice. Oh, I like that number too. Yeah, they're doing great. You could always just box without simplification if you don't want to simplify. Yeah. Okay. There we go. Good job. Yeah. Because we know what you're going to get when you do that. Yeah, you could just box that. I know what you're going to get. I mean, all right. Am I coming around to get yours? You're just. Yeah, that's wrong. Okay, but you've got it. You could wait. Where's K? K is there. Okay, and so then times 40. Okay, you could box that and hope for the best. I'll box it. Yeah, that's good. Good job. All right, Adric, did you box it? You're not going to box it. You're not. Oh, you did box it. Okay, good. Good job. Loving it. Anyone else? Are there others who are holding out on me? Oh, you are. Okay, you're holding out. Nice, nice. Okay. All right. Well, I have. I think I've got them all. Anyone else? Okay. So there were a couple of popular answers, both of which were correct, but one was more correct than the other. So, um, so here, let's. I'll show you what I have, and then I'll tell you the other almost correct answer. And then there's some that I think I'm going to have to look at closely to figure out what. Well, only a few. Only a few. So. Oh, that's not. Just a minute. That's what we're doing later. I was going to get homework ready, but here we go. Okay, so first things first, of course, you solve this differential equation, and I skipped a whole bunch of steps, this arrow. So it's t minus 21 is equal to some constant times e to the kt. Eventually you'll get that. And then I got the constant of integration was 75. So we all got that. I know everyone's like, yeah, this is what we got. Yeah. Okay, and then we get down here. Then things maybe went off the rails a bit. It says after 20 minutes, the temperature was 66 degrees. Okay, so you do this and you solve for K. And I got K is equal to, where is it? There it is. There's my K. I don't know what that is. Actually, I did. It's like some sort of weird. Do I have it? Oh, there it is. There. Okay. So there's my K. 0.02554. And then so here's what separates the correct answers from the almost correct answers, and that is a careful reading of this particular. In fact, it's this word right here. Sorry. so so if you got 48, you're almost correct, and I think that you deserve almost 100%. But the correct answer was 37.2. And when you plug in, so this is after plugging in 60. So if you plug in 40, you do get 48, which is almost correct. Okay. So anyway, there it is. But let's move on. Okay. So so today we're going to take a look at nonlinear models. Let me see. Do I have them here? Just a sec. Did I put them on the PowerPoint? Yeah, nonlinear. Oh, there it is. Nonlinear models. Nonlinear models. What are nonlinear models? Okay, well, these are models that are nonlinear, I guess. But in particular, so there's just a couple of them that are kind of interesting. So just to give you a quick plan of the next few days. So today, this is some nonlinear models, in particular the logistic growth model. Then on Wednesday, we're going to do mixture models. So this is when you're mixing up your latte. How much milk do you put in with the coffee, that sort of thing. So we'll deal with that. And then I don't know what we're going to do Friday, but for sure we'll do mixtures on Wednesday. They're fascinating. Okay, so nonlinear models, logistic growth. So what we're talking about here is we're talking about a more realistic. So up until we get to logistic models, you have this situation. This is exponential growth. So exponential. Okay, there it is dp over dt is equal to some constant times p. So that's called an exponential growth model, and that takes into account the fact that we have babies at some sort of a rate that is proportional to our population. People die at a rate proportional to the population, so that the population will either increase or decrease at a rate proportional to how many people we have. If you have 1 million people, there are going to be many more babies than if you have 100 people. So same thing goes with people dying. You're going to have more people dying in a population of 1 million than you do in a population of 100. So that's an exponential growth model. The problem with an exponential growth model is that it doesn't take into account the limited resources that populations usually have to contend with. So for example, if you have a population of deer living in Mount Vernon, there are only so many plants in my garden that the deer can eat. And so because of that, they run out of food after, if you have too many deer. And so for that reason, we have this logistic model. So that's the difference between exponential and logistic. Logistic growth is proportional to population for small populations. So this is when the population is small. But when the population gets too big, you run out of food. So then when it's too big, there's some limit. So this is some sort of a max population size. So logistic, let me just get the right letters here. Yeah, we'll use a giant K, sure. I think that's what I see there. It's kind of hard to, let's see. Let me just see what this has. Oh, no, I don't like that at all. Okay, well, here, let's do it the way that, and then we'll switch over to the books method here in just a sec. So the easy way to think of it is you have the growth rate of change, so this is growth, so the rate of change, is equal to some constant times the population size. That totally makes sense there. But then here's where things get a little bit funky, and that is that there is a max population size. And so that max population size, I guess we're going to use some sort of a giant K. Okay, we'll use a giant K for that. I don't really like it, but whatever. So, so the way that I'm going to sort of encode that is I'll do this. There. Now check out what this means. What this means is, if you think about it, oh, you've got big K and little k. I don't like that at all. Hold on a minute. Let me just, I'm going to have this. Oh, R. Okay, I get it. Okay, never mind. I guess I can change this. Okay, just a sec. I'll use little r. Yeah. Change this to a little r so it doesn't get confused with the giant K. Here, I better, here, I'll change this to a little r up here as well. So here, r. So little r is the growth, hold on a minute, rate. There, how's that? So the growth rate is little r, and then the K is the maximum population size, the giant K. Okay, now imagine what's going to happen when you have a small population. So let's say that we are living on a planet that can handle 10 billion people. 10 billion people is the maximum number of people that can live on this planet. I don't know if that's the case, so don't quote me on that. But let's say that's the case. And suppose we are living in the 1900 when there were 500 million people on the earth. Well, 500 million is very small compared to 10 billion. And so this number will be very small. And this whole term, 1 minus a small number, is pretty close to 1. And so that really doesn't play into the growth of the population. The population growth will be pretty close to exponential. So if you're pretty far away from the maximum, you're going to be, just like, let's keep growing. Let's do this. Let's grow, grow, grow. The closer you get to the maximum, the bigger this becomes, which tends to make this smaller. So the closer this will be to 1. So if the population is, say, 9.9 billion, and if the maximum carrying capacity is 10 billion, then 9.9 over 10 is very close to 1. 1 minus that is almost 0. And that means that the rate at which the population will increase is much smaller. So I guess I can do that. I can call K is equal to the carrying capacity. Okay, so I suppose that I've spelled that incorrectly, but it might help remember what it is. So anyway, there it is. So I suppose the next thing we want to do is we want to solve this nonlinear growth model, this logistic growth model. So let's go ahead and solve this. And to solve it, we're going to solve this slightly rewritten version. In fact, I'm going to do this over on Notability because it's much more fun. So here's what we're going to do is change this like here. I'll write down the original. R times P times 1 minus P over K. So there's the original one. And then here's what we're going to do is we're going to make slight change. So here's how this is going to look. R minus R over K times P. And then we're going to rename these things because it ends up being a little bit easier later on. So here, let's leave the stuff in that we're not changing. I'm going to change that to A and this to B. So that became A, that became B. Other than that, it's all the same. Okay, so we need to be able to solve this thing. So first things first, let's do the separable. Even though this is nonlinear, this is a separable differential equation. You know the drill. We're going to rewrite this like this. 1 over P times A minus B times P is equal to, I guess dt. There's nothing left over there. So it's just 1. So far, so good, right? Okay, next thing we're going to do is we're going to integrate both sides. All right, let's do this. So let's find a volunteer to do this. It's not going to be too hard, is it? Here we go. Let's randomize this. Okay, so Cooper Stiegel, do you want to do one of those left or right? I don't care which. No, don't do that one. Do that one. Yeah, do that one. I figured you'd take the easy one. Come on. Yeah, it's just T. Very good. Yeah, plus C. Very nice. Okay, so it's this left hand that's going to be a problem. It is going to have some natural logs in it, but how is this going to look? That's the issue. So let me remind you how to integrate something like this. Actually, we just did this today in Calc 2. So this is going to be like a blast from the past. It's going to give you a lot of joy. So the way you do this is you use a technique that you learned back in Calc 2 called integration by partial fractions. No. Oh, wait, why am I putting a P up there? Here, let me remind you, A. Okay, it's going to be so much fun. And then B over A minus B times P. Yeah, so partial fractions, you remember, it's fun. Okay, maybe it's not that much fun. But it's a thing. It's a thing that you remember. Okay. Okay, so just to remind you, actually, it's a good thing we're reviewing this because later on, especially when we get to Laplace transforms, we're going to need to do this quite a bit. So we might as well get in the get in the swing of things now. Okay, so multiply everything by the denominator p a minus b times p. So you remember this, p a minus b times p. And what's going to happen on the left, you get 1. On the right, you're going to get a times little a minus b times p plus b times p. Okay, that's not too bad, is it? Now, here's where I might differ from the way you learned to do partial fractions. In fact, here, let's see, do I have this up here? Hold on a sec. Yeah, look at this. See, we just did this today, literally. So let me explain just briefly. You don't have to write any of this down. I just want to point something out. And that depending on how you learn to do partial fractions, you get down to this stage where you've got some expression is equal to a times this expression plus b times this expression. The way that the book tells you to do this is you collect like terms. So you have x on the left, ax plus bx on the right. So that means a plus b equals 1. And then 5 on the left, 2 times a minus b on the right are the constants. So 5 equals 2a minus b. You have to solve 2 equations, 2 unknowns. But the way that I like to do this, and I think I learned this from a differential equations book years ago, I don't know if it's in yours, but is you just pick a convenient number for x, and it's really easy to get your numbers for a and b. So we'll do that. We'll do it that way up here. So I've got this, and I'm going to pick convenient values for p, because the p is kind of like the x. So the p equals 0 is the first one. I'm going to get this, a times little a. So capital A is 1 over little a. Well, that makes things easy. Now, as far as the second one, the next value of p is a little bit harder to see, but I'm going to use this. If p is equal to little a over little b. And the reason why I'm choosing that is because then I get this times a. And this is all 0. So see how clever that is? If you put little a over little b in here for capital P, that becomes 0. And you're just left with b times a over b. And so that means that capital B is little b over little a. So let me zoom out. And we're going to get to the part that you really care about in just a minute, because I know you really don't care about this as much. And so that means that this integral is equal to the integral a. Let's see, that's going to be 1 over little a all over p plus b, and b was little b over little a. Oh, wait a minute. Little b over little a. Little b over little a all over a minus b times p. All right, now we can do this antiderivative, and I'm going to stick that up here once I get it done. But this antiderivative is pretty easy. You have to ignore all the a's and the b's. So pretend that they don't exist. We'll do these one at a time. Haven, what is the integral? Ignore the 1 over a. What's the integral of 1 over p dp? Yeah, the antiderivative of 1 over p. Natural log, yeah. Natural log, very good. So the 1 over a is constant, so we're just going to let that go along for the ride. So natural log of p, very nice. And now what about the next one? Let's find the next volunteer. This one's a little harder. Rachel J., what do you think of this antiderivative of this thing? And if you ignore all of those letters, it's really not too bad. Almost perfect. I mean, there's just one minor thing, but it's not. It's almost perfect. So we have b over a, good, natural log of a minus b times p. So I told you to ignore all of the little letters a and little letters b, but now we can't really ignore them because really you should have done substitution here, and u would equal this, du would be negative b times dp. And so there's a factor of negative b that has to be put into here somewhere. So it ends up being this. You get a negative and then 1 over little b. So that's what it really looks like. And so this stuff, once I collect all so cancel those little b's, and let's zoom out. And so this whole thing ends up being 1 over a, natural log of p, minus 1 over a, natural log of a minus b times p. Wow, so much work. All right, I think we've suffered enough. We've done most of the work here, but you can see that we're going to end up solving for capital P. And to do that, we're going to have to convert from natural logs to exponentials. So let me go back to PowerPoint land and show you the final answer. So you end up with, yeah, there's that. We just saw that. So here's the rest of it. So this step, if you're wondering where'd this come from, I multiplied both sides by little a, so that you have this. So this we got on the notability is where this came from. So I multiplied both sides by little a to get rid of those fractions, and I combined the two natural logs. And since there's a minus there, you're going to turn it into a division. So we've got that. And then you have this. So change from natural log to exponential. And the a and the c got combined and turned into capital or little c1, I guess. Almost done. So this is kind of a pain. So solve for capital P. That's not very fun. But if you do that, you get this down here. So this is the final answer to the logistic growth model. So it's just kind of interesting that just like with the exponential growth model, you have a formula that you can rely on. You have a similar thing here with logistic growth. Okay, so we'll have an example here in a minute, but it's kind of interesting to look at the graphs of this, because the graph of this, depending on what little a and little b are, and what P0, by the way, the P0 there, that's just that comes from figuring out the constant of integration. So yeah, there's a extra, yeah, there it is. Anyway, so that's where that came from. But so the interesting thing is we've got some graphs. Let's take a look at the graphs. So here's what happens, and this you can imagine this is what would happen in the population. If you start out, so this A over B is the carrying capacity. I don't know if you remember from the when we were setting this all up, A over B was capital K. Anyway, so that's the carrying capacity. And if you start out with a population above the carrying capacity, then everyone's going to die out until you get down to the carrying capacity. So if you have too many people or too much of a population, then the population starts dying and ends up right there. If you have below, actually this is below the midpoint between 0 and the carrying capacity, you're going to increase as if it were a exponential function until you got to that midpoint, and then you start slowly, like slowing down your population growth. And if you start above that, of course, you're just going to increase and level off asymptotically at the carrying capacity. So we have those three different situations. Really, these two are the same situation. It's just, are you starting below or above that midpoint? So let's see what we can do with an actual problem. What kind of problems you're going to have to on your homework? That's what you care about, right? So let's look at this one. Student carrying the flu virus returns to an isolated college campus, like MVNU, with 1,000 students, like MVNU. Well, we have a few more, but not that many more. If it's assumed that the rate at which the virus spreads is proportional not only to the number of infected students, but also to the number of students not infected, that's logistic growth, determine the number of infected students after 6 days. If it is further observed that after 4 days, x of 0 is equal to 50. So let's explain all the words, because there's a lot of words here. So we have a situation where we're going to have the rate. Let's see, the rate at which the number of people, let's do it this way, is proportional to the number of students who have the disease, but it's also proportional to the number of students who do not have the disease. So that's what all of the words mean. Let's see if I can highlight all the important stuff here. Anytime you see this word proportional, is proportional, you should think you're going to multiply by some constant. What is it proportional to? It's proportional to the number of infected students, but also to the number of non-infected students. And that's that right there. So that's where I'm getting my differential equation. So even though this isn't strictly, it's not quite the same description as the logistic growth model, I hope you see that this is exactly a logistic growth model. So you have this, basically this logistic growth. Let me clean this up just a bit. So we have dx over dt is equal to x times 1,000k minus k times x. In other words, if we go back, let's just go back really quick to our description of the logistic growth model. Where is it? There it is. Oh, I think it was on Notability, actually, where I changed the air. Oh, there it is. There. Okay, so here, I'll just write it like this. So dp over dt is equal to p times a minus b times p. Okay, so going back to those two numbers are the important numbers for this solution. So let's go back here to, where is it? There it is. Okay. Okay, so oops, sorry about that. So in this case, this number is little a, is 1,000k, and this number is little b. So suffice it to say that we don't have to go through the trouble of solving this differential equation again, because we already have a solution. It's back here somewhere. There it is. So as long as we can use that, we don't have to resolve our differential equation. So, oh, this has p sub 0 in it. So I guess I need to know what p sub 0 is for this. Does it say A? Oh, A student. Okay. You got patient 0. Okay, A student. Okay, so that means that P of 0 is 1. It's so sad for that one kid. It's all his fault or her fault. Probably his, because it's always a guy, isn't it? Come on, I remember what it was like. You know, your prefrontal cortex hasn't fully developed. The guys, the girls, they develop them as teens. But guys, you have to wait till you're 25 or so. But anyway, so P sub 0 is 1. So let's see, do I have this all written here? Yeah, there it is. So this is, I guess, in terms of x instead of in terms of, oh, I have it in terms of x here. Okay, so dx over dt is equal to kx times, so I've got all of that. And so this is after, you know what, that's so confusing. Let's get that formula. Just a minute. This is going to take just a minute to copy all this stuff down, because I know that you don't want me to just read off the slide, so we'll have to actually do it. Let's go back here. Okay, so there's that. And then we need the formula, because I don't have the formula memorized. Are you kidding me, this formula? So nasty. Where is it? There it is. Okay, so let's grab this formula. Hold on a minute. Done, copy and delete. Like if I really needed this formula, I'd probably have to rederive it from scratch, to be honest. There we go. Okay, so there it is. So let's go ahead and get our solution. So the solution is going to be x of t, not p of t. That's okay. A is 1000 k times p0. P0 is 1, that one kid that showed up sick. And then on the bottom I have b, that's k, times 1, plus, and then in parentheses, a minus b times p0. Wait, what was b again? B is k. Times e to the negative a. Sorry, I keep having to look. Times t. There. So there's my solution. Let me clean this up. 1000k. Okay, on the bottom, I guess I have k plus 999k e to the negative 1000 kt. Does that look all right? Okay, so now what else do we need to know what k is. It says after 6 days, wait. Oh, after 4 days, you have 50 students infected. Wow, so many students all of a sudden because that one kid that was so selfish came back too soon. Okay, so we have 50 students after 4 days. So 50 should equal 1000k over k plus 999k e to the negative 1000 times k times 4. So that's, just so you know, that's x of 4 is equal to 50. Oh, we only have 5 minutes. Or do we have fewer than that? Oh, we have 2 minutes. Okay, here, look. You can cancel the k so that you got 50 is equal to 1000 over 1 plus 999 e to the negative 1000, 4000. Okay. And then this, I hope you can see that that's a nice, I mean, you could isolate the e to the negative 4000k and solve for k, which I don't have time to do. Okay, so homework. When you do your homework, I've got a place online you can upload the homework. I meant to go over that. I want to experiment with this week. So if it's too much of a pain, I was going to demonstrate it with my phone, but I can't now because it's too late. But if you don't know how to do it, stop by tomorrow. I'll help you. It'll be fine. And I could even give you cookies. I've got a secret stash in my office. So try to go online, see if you can upload your homework. It'll simplify things for me. I know it'll be a little bit more work for you.